In the previous two videos, we looked at Laplace transform and step function. In this video, we will look at another special case in Laplace transform called short impulses and Dirac delta function. Very soon, you will see that they are related to what we learned previously of the step functions. Let's start by looking at a more general case. Say fk t minus a as the equation, which is equal to 1 over k if it's in the range between a and a plus k. It's zero otherwise. Then how it looks like if we draw that in a graph. Initially, the curve stays at 0 until it reaches a. And at a, there's a sharp increase to the value of 1 over k. And it stays at 1 over k until it's at a plus k value. Then it goes back to 0. What is special about this equation is that if we look at the area enclosed by this square impulse, that is k multiplied by 1 over k, which gives 1. Next, let's look at an extreme case. We have delta t minus a equals to infinity if t is equal to a, and it is 0 otherwise. We have one extra condition here. If we integrate the delta t minus a function, it gives us 1. If we draw the graph, the value stays at 0 first. At a, the value hits infinity, and as soon as you go away from a, it goes back to 0. Let's quickly go back to the second condition of this equation, that integrate delta t minus a dt is equal to 1. What this tells us is if we imagine the short impulse is a super slim rectangle, has nearly 0 width but infinity length, the area enclosed is still 0. The name for this type of equation is called the unit impulse function or the Dirac delta function. In the following example, we'll only focus on the Dirac delta function. If we perform Laplace transform on the Dirac delta function, it gives us e to the power of minus as. If we recall what we learned from the unit step function, the Laplace transform of the unit step function is e to the power minus as over s. So you can see the similarity and the differences between the Laplace transformation of the Dirac delta function and the unit step function. Here is an example. We have y double prime plus 3y prime plus 2y equals to delta t minus 1. The question asks you to solve y. You can see that on the left-hand side of this equation is a second-order differential equation. In real life, it can either represent a damped mass spring system or an RLC circuit. I hope you still remember R represents resistance, L represents inductance, C represents capacitance. On the right-hand side of the equation in the question is a delta function. It represents a hammer blow on the mass in the mass spring system or a voltage spike in the RLC circuit. T minus 1 in the Dirac delta function is that the action, either the hammer blow or the voltage spike, happens at time equals to 1. To solve the question, we'll start by writing down the subsidiary equation, which is s squared plus 3s plus 2 capital Y equals to e to the power of minus s. The e to the power of minus s is the result of the Laplace transform of the Dirac delta function delta t minus 1. At the left-hand side of the equation, s squared plus 3s plus 2 can be broken down into s plus 1 multiplied by s plus 2. Rearrange the equation. Factorize what we have here. Then perform inverse Laplace transformation. You will get the answer. The response to the Dirac delta function is 0 if t is between 0 and 1, and it's equal to e to the power of minus t minus 1 minus e to the power of minus 2 t minus 1 if t is greater than 1. Finally, we can draw the input and the response together. For the input, it's pretty straightforward. It's just a unit impulse at time equals to 1. The magenta colored curve shows the response. Initially, it's at 0. When time equals to 1, it starts to respond to the impulse. It increases initially, then tails off. From the shape of the curve, we can tell it's an over-damped oscillation. The next video will be the last one for Laplace transform. We'll look at convolution and Laplace transform.